In an array designed with balance and symmetry, one element breaks the rule by repeating again and again. Welcome to this presentation on the problem n repeated element in size 2 an array. In this session, we will clearly understand the problem, analyze the constraints, and arrive at an optimal and elegant solution using observation rather than brute force. Let us first understand the problem. We are given an integer array called nums. The length of this array is exactly 2 times n. The array contains n plus 1 unique elements. Out of this, exactly one element is repeated n times, while every other element appears only once. Our task is straightforward: identify and return the element that is repeated n times. The problem may appear simple, but the constraints allow us to do much better than a basic frequency count. Now let us carefully analyze what the constraints imply. The total number of elements is twice n. The number of unique elements is n plus 1. This means one element appears n times. The remaining n elements appear exactly once. So effectively, half of the array is occupied by a single repeated value. This dominance is the key insight of the problem. An element that occupies half the array simply cannot stay isolated from itself for long. Let us look at the first example. The input array is 1, 2, 3, 3. Here n is 2, so the array size is 4. We have 3 unique elements 1, 2, and 3. The element 3 appears exactly twice, which is equal to n, so the correct output is 3. This example already hints that the repeated element tends to appear close to itself. Now consider a slightly larger example. The input is 2, 1, 2, 5, 3, 2. Here n is 3 and the array length is 6. The element 2 appears 3 times while every other element appears only once. Once again, the answer is the element with frequency n, which is 2. Even though the repeated values are not all adjacent, they still appear within a short distance of each other. A very natural first thought is to use a brute force approach. We could use a hash map, count the frequency of each element, return the element whose frequency is equal to n. While this works correctly, it has drawbacks. It uses extra memory. It ignores the strong constraints of the problem. It is not the most elegant solution. Given that this is an easy problem, the expected solution is simpler and more efficient. Here is the turning point of the problem. Since one element appears n times in an array of size twice n, it is mathematically impossible for all its occurrences to be far apart. At least 2 copies of the repeated element must appear next to each other or very close to each other. This observation allows us to detect the repeated element without counting frequencies. Based on that insight, we can design an optimal strategy. We traverse the array once. For each index I, we compare nums I with nums I plus 1, nums I with nums I plus 2, nums I with nums I plus 3. If any of these values match, we have found the element repeated n times. This works because duplicates are guaranteed to appear within a small distance. Why do we only check up to a distance of 3? Because the repeated elements occupy half the array. Even in the worst possible arrangement, the pigeonhole principle guarantees that 2 occurrences must fall within 3 positions of each other. This is not a heuristic, it is a mathematical guarantee given the constraints of the problem. Let us summarize the algorithm. Step 1. Iterate through the array from left to right. Step 2. For each element, compare it with the next 3 elements. Step 3. The moment a match is found, return that value. The problem guarantees that exactly one such value exists, so we will always find an answer. Here is the C++ implementation of the solution. We loop through the array once. At each index, we check 3 comparisons. As soon as a match is detected, we return the current element. If no match is found, which will never happen due to problem guarantees, we return -1 as a fallback. This code is clean, efficient, and uses no additional data structures. Now let us analyze the complexity. The array is traversed only once, so the time complexity is big of n. No extra space is used, so the space complexity is big of 1. This makes the solution both time efficient and memory efficient. Let us compare this approach with other possible solutions. Using a hash map also takes big of n time, but it requires big of n extra space. Sorting the array uses constant extra space, but it increases the time complexity to big of n log n. The distance check approach achieves the best of both worlds, linear time, constant space. That is why it is the most optimal solution. The key lessons from this problem are: always pay close attention to constraints. A dominant frequency almost always implies proximity. Elegant solutions often come from observation and not from brute force. This problem is a perfect example of how thinking beats memorization. We have now seen how a simple observation transforms a seemingly basic problem into a clean and optimal solution. Thank you for your attention and happy coding, and keep practicing problem solving with insight.